Thanks. Yeah, it's great to be here. Great to see everybody. Great to meet new friends. And hope we see you all in future conferences as well. So, yeah, I've been, for those of you who don't know me, I'm a biologist. I've been working on large mammal systems in northern Canada for probably 25 years now. I'm a consulting biologist, work for a variety of industries. My participation here today is being partly paid for by the Forest Products Association of Canada. So I'm very grateful for them for sending me here. And probably 70, I've talked on a variety of species over the years, but probably 70% of my work is on caribou, which is here on the left-hand side. Caribou are the North American version of reindeer. We have reindeer in Europe, in Scandinavia, and in Asia. The North American version are caribou, and they range throughout northern Canada and into Alaska. I study the ones that live in the woods, not the ones that are out in the tundra and those big giant herds, because there's lots of those around as well, but I study the ones that live in the woods. And I searched my hard drive. My earliest Bayesian network is September 2003. So I've been playing with Bayesian networks for quite a while, but things really ramped up when I attended the Bayesian conference in 2014. This was the one in Los Angeles. And between Felix's course on directed acyclic graphs and Lionel's presentation on using Bayesian Lab in a causal context, and also having a inspiring keynote presentation from Udaya Pearl at that conference, it really flipped something for me in my head, because it really crystallized for me a problem that I see commonly in my field of research. Because when you're dealing with these systems, we can't do experiments. We're always dealing with observational data. We can't just take a giant piece of land and randomly assign a treatment and then wait 25 years to see what happens. So we're always dealing with observational data. And I think that my field actually has a big problem with managing the correlations. And it's one of those things that I've been kind of evangelizing against, I guess, now for 10 years. Makes me kind of not very popular sometimes, but once you take the red pill, you start to see this stuff everywhere. So every field has its analysis paradigm. In the field that I work in, there's a lot of GLMs. It's basically a generalized linear model world where we have buckets of predictors, and we are looking for the most parsimonious fit to our data. Everybody does kind of the same thing, but we have a big problem with equating parsimony with cause. And it drives me crazy all the time. And so one of the things that we've been doing quite a bit is looking at rates of habitat, what we call habitat disturbance. So what is it people are doing on the land base that are creating disturbances, and correlating that with various measures of the performance of animal populations. So in this slide, for instance, we have on the left recruitment. So recruitment is just the term we use for how many young animals are being recruited into the adult population for breeding purposes. So that's called recruitment. Higher the number, the more young animals are being recruited. So it's a measure of population growth. And then anthropogenic disturbance, how much of their range is being disturbed. And this is colored up also by fire, because fire, of course, is becoming increasingly important, as many Americans know from the smoke that we sent you last summer. You're welcome.
Sound check. Can you hear me?
Actually, people in Seattle are used to that. Every summer they get a couple of weeks of Canadian
Can you hear
smoke,
me?
but it happened in New York City. So now
I don't think we can hear you yet.
Change is real. Amazing how that happens. But
you're
to give you
very
an idea
quiet.
how deep this is, I just wrote a paper. I got a comment on the paper from one of my colleagues, and I kid you not, this is what he said. He said,
"Can you
"We
speak up a little
understand the
bit more
potential
loudly?"
hazards of assuming causation from correlative analyses. However, in this case, it is unclear why the available correlation is insufficient." I thought, you've got to be kidding me.
Can you speak
just
up?
answered the question. It's never sufficient, precisely because the dangers of correlating or mistaking cause and correlation. But I think that more than anything, people just haven't been exposed to the tools, and they just kind of throw up their hands and say, well, we're doing the best we can. It's like that's all we've got, so we've got to work on it. So this is what I've been trying to get across. And so this culminated, I was able to publish a paper a couple of years ago, and really it was just the way of explaining to biologists in my particular field how to distinguish rung 1 from rung 2. And if you're going to start talking about interventions, that we need to introduce from observational data, we need to introduce a causal model, we have to do our causal identification. In some cases, we can't identify those causes, and just introducing those concepts. And a lot of good feedback on the model. Everybody says, huh. And it's actually a pretty easy way to get a paper. If you just take whatever fields you're most familiar with where these techniques have not been applied yet, and just, beg, borrow, and steal from some of Pearl's books, and it's a pretty easy paper. So yeah, that was about distinguishing rung 1 from rung 2, but of course there's another rung. And so that's what I've been working on for the last couple of years. I kind of introduced this last year. This is kind of a continuation of that work, and just explaining what we're gaining when we're going to rung 3. And Pearl himself in his Causality book says, policy analysis is an exercise in counterfactual reasoning. And so and I thought, wow, that's a pretty bold statement. So we need to have counterfactual reasoning in order to do policy analysis. And that's the world I'm living in. I'm trying to take the data that we collect and really make recommendations to policymakers about how we should be managing our landscapes, these multiple use landscapes where we have a lot of things going on. And so the toy example that we always use is this idea of an aspirin, right? You're taking an aspirin. And so our policy option might be, if you have a headache, take an aspirin. That's the policy that we want to evaluate. And of course, there's a couple of questions around that. If I have a headache, will taking an aspirin cause it to go away? So that's the classic interventional rung 2 question. And in this case, we're looking at what's the effect of the cause, basically. So what's the effect? The effect is headache goes away, of a cause, in this case, taking the aspirin. Of course, there's the second question, which is, if my headache went away, is it because I took the aspirin? So now we're reversing that. Now we have observed the effect, headache going away, and we want to know whether we can attribute that to taking an aspirin. And when you first look at this, in some cases you might think, okay, well, the first one is prospective, the second one is retrospective, but is there what further insight are we getting if we go to that question 2? And in some cases, you're not really gaining anything. So if this was direct and causal, and aspirins were 100% effective, and nothing could ever make a headache go away except aspirin, then both 1 and 2, if the answer to 1 is yes, then the answer to 2 is yes, and it's probably a good policy option to undertake. But the question, of course, is, well, what if aspirins aren't 100% effective? What if they're 60% effective? Is it okay? Do we still need to answer both these questions? And the answer is, well, it's still probably a pretty good policy to take an aspirin, but as long as aspirins are cheap. And I think that's the key around this second question, is if aspirins were $500, you'd want to make sure that if you were going to take an aspirin, your headache just wouldn't go away for some other reason, and I wasted taking an aspirin. I think as soon as we get into this situation where the policies are expensive, where the interventions are expensive, we want to talk about the probability of having the same outcome for reasons other than the intervention. And that's where the key comes in this counterfactual reasoning, which is related to this question 2. So what question do we have to answer? We have to answer the question, if I hadn't taken the aspirin, would my headache not have gone away? So now we're talking about things other than what we did to understand causation. So in this framework, to understand causation is not about the effect of something that we're doing, but basically the effect of what we didn't do. And that's what we have to dig into. And so this is the piece that I want to try to bring to my research, is talking about these counterfactuals and how they can inform policy. I'm still working through how to kind of formulate in the best way, but that's kind of the theoretical background. And that leads into these very important concepts: necessary and sufficient causation, where necessary causation, probability that an outcome would not have occurred in the absence of an event given that they both did occur. So that word salad is basically saying, what would have happened if I hadn't taken the aspirin, and what's the probability my headache wouldn't have gone away if I hadn't taken the aspirin, given that I did take the aspirin and it did go away. sorry for, I apologize before for people whose first language is not English, because there's a lot going on in that sentence. And of course, there's the other side of that. If I didn't take the aspirin and my headache didn't go away, what's the probability that it would have gone away if I had taken the aspirin? And then you can put those two things together. And what we really want to do when we're implementing a policy, we want to make sure that the policy that we're implementing is necessary to produce the outcome that we want, and that we don't want to waste the effort in something that we might have the outcome anyway, even though we didn't put that policy in place. Okay, one more slide, and then we'll talk about the caribou system. So as we move from this rung 2 to rung 3, and this is how we relate this all back to Bayesian networks. So a lot of Pearl's examples and examples elsewhere are not necessarily taught. Doesn't really often talk about rung 3 in a Bayesian network perspective, which is kind of interesting. But if we, in this kind of simplest case where we have some sort of exposure and an outcome, we know what the DAG looks like, and these U factors, of course, when we're developing the causal model, we want to make sure that the U's, these are the kind of the, I guess, what would we call them? They're the error, basically, that are produced by the unique circumstances of individuals, of course. And we want to make sure those are uncorrelated. If they're correlated, then we probably don't have the models. We want to make sure they're uncorrelated. But the individual U's become very important when we're talking about counterfactuals, because we're no longer talking about average effects. We're talking about how I respond when I take an aspirin, not necessarily how everybody else responds. So we're moving from average effects to these kind of individual effects. And so we need to know those U's. The problem is, you know the U's in a deterministic framework, and you can actually calculate the counterfactuals directly if you have a deterministic model. But once you move into the probabilistic world, we no longer have access to those U's for individuals. So basically, we have to make a series of additional assumptions. Okay, causal effects from observational data. So as we're moving, the basic message here is that as we're moving from observations to interventions to counterfactuals, we're increasing the amount of information we need to know about the system. So observations, all we need is enough data to correlate two variables together. We've got an observation there. If we move to this interventional piece, then we have to discuss the causal model, and we have to make sure that our causal effects are identifiable. If we're staying in this observational universe, when we move to the counterfactuals, there's a couple of additional assumptions we have to make. And Pearl works out the theory for this in the 2009 book. The first thing is that the exposure has to be exogenous, so basically no incoming links to the exposure. And also the effect has to be monotonic. And what he means by that is that everything has to act in one direction. If you take an aspirin, it can only take away your headache probabilistically. It can't actually give you a headache. If you can make that assumption, that monotonic assumption, then you can work out the counterfactuals for your particular system. So that's the framework that I'm working in, trying to apply these concepts to understand how I can calculate counterfactuals in my system and how can work to improve decision making. Okay, lots of theory. So some pictures. So I'll tell you briefly, this is give you an idea. So I showed you a picture of the caribou. They're running around this is the boreal forest in northern Canada. The blue pin shows where I actually took this picture out of a helicopter, and that's a seismic line. And a seismic line is used for geophysical exploration for oil and gas purposes. And in the old days, pre-GPS, they used to just use D8 cats and just plow these seismic lines through the boreal forest, basically horizon to horizon. This is actually a little video it should play. Let's just try that again. If my video won't play, then that's a disaster, isn't it? Isn't that weird? What's that? Is it what image? Satellite image? That was a satellite image, yes. Let's just try this. See, now it'll play on here. At least it should play. Well, what a shame. I won't play that. But anyway, the problem here is that these lines accumulate. So this is a section of northern Canada, and I've highlighted in white all of the lines that have accumulated over the years. And these lines don't go away very quickly because this is all boreal forest. It's very spongy. Growing season is very short. Sometimes these lines can last 50, 100, 150 years. So over the decades, they all start to accumulate and you get these very high densities. And that's just from the oil and gas exploration. These are forestry cut blocks here. So these would be a few hectares in size, just to give you the scale. I don't have the scale on here, but it's a huge area. Those are dotted with little lakes, lots of wetlands. No towns, no roads, but lots of these various lines. And so this is the environment that we're working in. And again, that's what it looks like on the ground. You can see that some of these old lines are bladed horizon to horizon. They go on for kilometers. And what happens is they become highways for predators. And so here's a grizzly bear in the bottom right here, and wolves in the top right. And these predators will use these lines as highways, and they penetrate deep into caribou habitat, and they kill caribou much more frequently. These are from trail cameras. So trail cameras have been a real advance in what we're doing. You think cameras, that's not very advanced, but these motion activated trail cameras that we can put in the woods, we can deploy them, put hundreds of these cameras on in these huge grids to monitor how animals are using them. This is another video. There we go. This one's working. So this is just some pictures. These are still images from the videos, from these trail cameras. And so they record, they're infrared at night, so you can see all the animals using them. So here's some caribou moving through. Caribou do it, they live in these kind of small bands. There's a big moose. I've got another one. A group of caribou moving through. Here's a group of wolves. So yeah, it's a tremendous tool to be able to capture this kind of information and discern how these animals are using these various lines. So what do we do about these lines? And the answer is we have to treat them somehow to get rid of them. And what we usually do, because to try to get these lines back on a trajectory where they can actually be restored, you have to take some heavy equipment in the winter. You have to have freeze-in conditions, and they basically rip up these lines and they produce these mounds, and then they plant trees on top of the mounds. So it's extremely expensive. So this would run probably $10,000 a kilometer. And there's hundreds of thousands of kilometers that need to be treated. So this is a tremendous cost to put these lines back together. And so from my perspective, and from the perspective of a lot of my clients, including government, if we are actually going to make this massive investment in these restoration efforts, we need to know that they're going to be effective. And it's going to take this tree a very long time to grow. So we're not going to know for a very long time. So then the question becomes, so this is a question of regret. This is where the counterfactuals come in. Are we going to regret doing this in 50 years? How confident are we that these kinds of actions are going to be successful? And so then we have to think, okay, well, what's the probability that putting the lines on there made the caribou go away, or was responsible for these declines in the caribou that we're seeing now? How can we attribute that to those lines going on there? Because if they didn't cause the caribou to go down, then if we do all this effort, it's unlikely that it'll cause the caribou to come back. And so that's the kind of thing that I've been struggling with and trying to understand work through. And so this is just a reformulation of that relationship I showed you earlier, where we have this habitat disturbance along the x-axis and this measure of calf recruitment on the y-axis. And so basically anything above that horizontal line, caribou are doing well. Below that line, they're doing very poorly. And the vertical line, we want, the current management effort is to make sure that all of our ranges have very low disturbance. So they're over on that side. And so if you just graph this into these 4 quadrants, what you find is, yeah, we have a lot of ranges where we have lots of disturbance and those caribou are doing very poorly. They're all going down. We have much less evidence in the top left, your left, top left, that we have caribou in low disturbance ranges that are actually doing well. We don't have, most of them are going down. And the problem that we run into are the ranges that are running counter to our hypothesis. So in that bottom left, we have a bunch of ranges where the caribou are going down anyway, even though they don't have a lot of disturbance. So these are the kinds of things we're thinking about. Okay, if we've got ranges where they're not heavily disturbed, but they're going down, that suggests that maybe those lines aren't necessary to cause the decline of the caribou. And in the top right, we have a few ranges where they're in a very high disturbance environment, but they seem to be doing just fine. So these are the pieces that we need to understand, and that really speaks to this idea of what's necessary and what's sufficient to cause these declines. So one of the things that I try to tell my colleagues is that, well, if you're going to run off of this correlation, you're really assuming a causal model. You may not be explicit about it, but you're really just assuming that this is a direct relationship, causal relationship between our treatment or exposure of disturbance and the outcome that we're looking at. And that's the implied causal model that we're working under. And from just that very simple model, we can go through these very simple equations to work out both the factual side, so what actually happened, and then the counterfactual side of what would have happened if we had not made that exposure, for instance. And so we've got these 2 worlds. So this is very simple just to do the calculation, but on the top we have the factual world. So we condition on that treatment of high disturbance and we can see what the outcome was. And then the counterfactual world, it's just doing the opposite. And then we can do our 3 calculations of probability of necessity, probability of sufficiency, and the probability of necessity and sufficiency. And once I do that, I come up with 17.6%. So that suggests to me that on average, the probability that the imposition of all that disturbance was both necessary and sufficient alone to cause that decline in caribou was only 17.6%. So that concerns me because I think, well, there must be some other stuff going on here. And if we do this, I'm concerned that we're going to make this huge investment and we're not necessarily going to get the benefits to the caribou that we want to see. And it's a complicated system. It's not just this kind of naive correlation between disturbance. There's a lot of things going on. There's fire effects. Yeah, we're doing lots of logging. There's oil and gas exploration. We've got lines. We've got cut blocks, and they're serving the system in a different way. So for instance, as I said, the predators like to use these lines as highways. They become predator highways. But when we have forestry cut blocks, that's making actually lots of food for moose. And we get more moose in these areas, and then we get more wolves, we get more moose, and then the wolves eat the caribou. And so there's all these things going on. We need to start teasing this stuff apart and trying to do a better job of getting the causal relationship straight. And so I just started to pull apart this idea of disturbance and say, well, like I said, we've got these lines, but we also have cut blocks. What's going on here? And so I just graph this, our linear feature density, kilometers per square kilometer, versus the percentage of the range that we have in cut blocks. You can see, first of all, they're not very correlated. So basically in those places we have lots of lines, we don't necessarily have lots of cut blocks, and the other way around. The stable populations, if they're not stable, it's in red. If they are stable, they're in blue. And you can see all the blue ones are stuffed down in the bottom left corner. So there's something going on with this landscape effect. We have no evidence that once we get above a density of about 0.2 kilometers per square kilometer, we have no evidence that those caribou populations are stable. So there's probably something going on there. If we get more than 10% cut blocks, we have no evidence that those herds are stable either. So those are kinds of natural management thresholds that come out of this. But if you notice that in that bottom left-hand corner, they're not all red, they're also blue, which means that even if you do all the work to stuff the landscape conditions into that bottom left-hand corner, you still don't have enough. The conditions are still not right to guarantee that you're going to get, well, there's no guarantees, but to really bring about the idea that you can recover caribou with a high probability, even when you're down in that bottom left corner. So the one other thing that I brought into this analysis was landscape productivity. So not surprisingly, caribou like the north. They're like Santa's reindeer. They live in the North Pole. Well, they don't live right in the North Pole, but they live up north. They're animals there's no caribou in the lower 48, for instance. And so they tend to do well where we have unproductive habitats. And so I classified this in terms of a certain threshold that I chose for this measure of landscape productivity called EVI, Enhanced Vegetation Index, I think is what it's called. Those brown ranges are unproductive. The green ranges are more productive. And I found that there was only one of those green ranges where caribou were stable, but in the brown ranges, about a third of them were stable. So again, there's this kind of natural break in landscape productivity, just like there is in those disturbance features. Okay, another video here. So here's some caribou. This is a little break. You can see them. This was a project that we had where we were doing some supplemental feeding to see if we could fatten them up so they could run away from wolves a little better. It seemed to work, actually, oddly enough. This guy's lost one of his antlers. The males both males and females have antlers, but the males have bigger antlers. They lose them every year. That's one of the feeding stations that we had. They did it. It was quite interesting. In this area, they not only had feeding stations, but some of the feeding stations they had hooked up to a scale. So in order for the animals to get to the feed, they had to step on the scale so they could monitor their weight gain over time, and then had a remote camera. There's actually a live YouTube feed of this area. They're not in this. They're only in this area in the winter, so they're not there right now. But there's a live caribou cam. You can go watch them feed and stand on the scale. So it's kind of fun. Okay, back to the science. So one of the things so this is kind of the next step that I've gone with this, which is just to start to separate these different sources of disturbance and this concept of this landscape productivity and build a causal model. Do that in Bayesian Lab. Very simple. It's still an extremely simple model. But of course, you have to make assumptions. You have to assume you have no unobserved variables. And instead of setting a target node to make sure the links were oriented correctly, I set the temporal indices. And then I had to make a couple of adjustments. But basically, it's still very simple to learn this network. The one thing I haven't talked about again is fire. And you'll notice that fire isn't really hooking up in here, so it's not coming in as a significant predictor of recruitment. And which you might find strange, but actually the boreal forest is always burned. Like it's a very, very high disturbance environment. The boreal forest traditionally would burn maybe once every 80 years. So at any time you'd expect a good portion of that forest to be charred. Now we've modified that through our own behavior, so we suppress a lot of fires. Not so much in the far north because those fires are just too big and they cost zillions of dollars to suppress. So a lot of those we've let burn over the years, but the closer you come south, the closer you get into infrastructure, the more fire suppression we've done. And the problem now, of course, is that those fires are burning a lot more intensely because there's a lot more fuels. And we think that as these fires become more intense, they actually get much worse for the caribou because they burn a lot more of the duff on the ground. Things are much, much slower to regenerate. So just a couple of quick things I wanted to point out. So what I did is I had this original model, which is the one up there in the yellow. Probability of necessary and sufficient causation on the right-hand side, only 17.6%. What I found on that first green line that is if I if I just separated those sources and separated the linear features from the cut block and added this landscape productivity, I could get that up to almost 30%. So now I've almost doubled the probability of necessary and sufficient causation. So we're doing a lot better. We're doing a lot better, but still not doing all that well. There's obviously a lot that's going on in the system that we can't explain. But just by playing with the model and setting those thresholds a little bit differently, bringing another variable, I can do better. And then the one thing that I found is that the way it was applied was different depending on where we were. So in these brown ranges, it was up to 55%. So basically what I'm saying here is that in those places that are unproductive, if you put lines and cut blocks on the ground, it's really bad for caribou. But if you're in the green ranges, it hardly makes any difference. And I think that's because these green ranges have a lot of forage, they have a lot of moose, they have a lot of wolves anyway, they got elk, they got deer, there's a lot of things going on, and it's just a hostile place for caribou, and it's getting more hostile with climate change. So there's all these drivers in the more southern areas that are making things worse, to the point that if you put lines on there, it really doesn't contribute very much. So this is talking about moving from average effects to really understanding maybe we shouldn't be doing the same thing everywhere. We should be focusing our efforts in those places where it's most likely to make the biggest difference. And that the only way you can start to do that, moving from average to individual effects, is moving from that rung 2 to rung 3. So that's the way I'm starting to think about that. Okay, just starting to wrap up here. So in terms of the implications for caribou management, so these are the kind of slides. Our current model has low causal attribution. If you just use this giant bucket of disturbance and you're going to use that to try to drive caribou recovery through restoration, it's only 17% is the driver. So there's not much, we're not going to have a lot of success with that. But once we start separating out this habitat disturbance in these different pathways, setting some different thresholds, then the attribution starts to go up and we're doing a better job. We can target our restoration in places where it's most likely to be useful. Although still, there's other things, we can only get so far. But eyes wide open, right? So as long as the policymakers are aware of that, I think that we've actually advanced things a bit. And this is one of the ways, I think that Pearl talks about this in one of his papers, is that necessary and sufficient causation apply differently to different groups, different stakeholders, shall we say. So necessary causation, does an outcome require an action to have occurred? That's where researchers, that's where we spend all of our time, basically. That's why we spend all of our time on rung 2. What is that intervention necessary to see the outcome? That's where we spend our time. Lawyers spend a lot of time in this as well, because they want to prove that something, some event was the cause of something. And then advocates as well, because they want to assign blame. So they're all kind of working in this necessary causation world. The sufficient causation world, this is really the world of planners and managers. And so they want to know, well, yeah, sure, A might cause B, but maybe some other things cause B as well. And we want to make sure that we just want to get to B. And so maybe there's a bunch of different ways to do that. So let's talk about kind of the big basket of things that we might do to get to the outcome that we want. They're outcome focused, and the necessary causation people are more, intervention focused. But of course, the policy makers want to know both sides of this. They want to know not just if A causes B or how we can get to B, but they want to be able to implement effective actions but avoid the unnecessary and particularly the costly actions. So I think it's really important that if we are making recommendations to policymakers, that we're looking at both sides of this the causation equation, or else they're really not being fully informed. And I think this is one of the key pieces. And so we see this all the time. Again, with the fire example, people argue all the time, right? Well, that fire would not have occurred if it wasn't for climate change. And then someone else might say, there's lots of things that cause fire. It might have occurred anyway, even if there had not been climate change. Both those are statements of causation. They're both true to some extent. And what they're really doing is arguing causation from either a necessary or sufficient perspective. And knowing both of those perspectives and reconciling those, I think is a big mission that can help bring some of these severe policy debates together. So just to remind everybody in the room who's interested in this piece is that I think it's really important when we move from interventions to counterfactuals. Super important when those interventions are costly. If it doesn't cost you anything to do the intervention, then it really doesn't matter, but it's costly, it's important. And it really enables us to target policies, moving to try to identify where those policies are going to have the greatest effect. But in doing so, we have to have either more knowledge or we have to make more assumptions about a system. One more video for you. Okay, so this is, I don't know if I've ever shown this one before, but here's the helicopter. This is not me, but this is from outside the helicopter. This is what they do to capture caribou. This is this is mountains in northern BC. So he's got a net gun. He's hanging out of the helicopter. He's tethered to the helicopter. And then that's the guy who's wrestling the caribou to the ground. They don't use any drugs for this, which is super important because if you don't use drugs, you don't have to reverse it. It's much safer for the animals, but they actually do quite well. So that's Diane Culling. She's extreme. They've done this thousands of times, extremely good at it. The most dangerous thing is when you're releasing them. So you see how careful they are because you really get kicked in the head and that's not a good thing. But yeah, caribou are small enough that they can actually be wrestled. And you see you can see she's got a radio collar on now. And she doesn't seem any worse for wear. And her friends were just standing around watching what was going on. They're not the brightest animals, that's for sure. But yeah, she's just kind of shaking her head and saying, well, that was weird. Kind of carrying on. So if you get into the moose, actually, the moose have to be tranquilized. And to tranquilize moose, we've always used this drug, fentanyl. I don't know if you've heard of that. It's true. It's what we use for moose and larger animals. We use fentanyl to tranquilize them, and then and reverse them too. So they'll use because it's extremely dangerous because moose are huge animals, 1,500 pounds. So it takes a lot of tranquilizer to bring one down. You process the moose, and then you basically give them the naloxone or whatever it is to reverse it, and then they get up and say, "Wow, that was weird." But yeah, for the smaller animals, we don't have to do that, and it's much safer. A lot of people are still quite concerned about even just the caribou wrestling, obviously, because there is the occasional injury, but they're pretty good with it. But a lot of work now, of course, it's all switching to cameras pretty much, and just because it's much cheaper, and you can collect a lot of data in a short time on multiple species. So I'll stop there. Happy to take any questions.